All right, here we are with area and perimeter with coordinates 4.09 exit ticket. Take some time here to recognize the name of this particular equation. You should have selected distance formula. You can see it's the square root of the sum of the square differences of the x and y coordinates. That makes it the distance formula, which we've been working with throughout the week and previous week. What we're doing today, again, kind of what we did last week as well, is we're going to be working with perimeters and areas of rectangles, triangles, and polygons, as well as areas of composite figures or composite figures using coordinates. And so to that end, we're going to review from Friday's lesson, go over some perimeter example problems, some area example problems, and then we'll be looking at the exit ticket 4.09. So reviewing from last Friday, we have our distance formula here with our x and y coordinates, x1, y1, x2, y2, and of course we know the distance formula is there. We need to utilize that formula to determine the lengths of certain polygons or figures like rectangles and triangles. And that allows us to determine the perimeters and the areas of those figures, as we can see right here with the rectangle and the triangle. So looking at this example right here, we have to determine if we need to find the distance of RS or QT or RQ or ST, and we find the perimeter and add up all of those sides, right? So in order to do that, we want to first target one of our particular lengths. I'm going to go ahead and focus on doing QT in this case. So for QT, we have a length that we can calculate by doing our distance formula. So here I'm going to have my 5 minus negative 3 quantity squared plus our negative 6 minus 0 quantity squared. There I end up with 5 plus 3, and since I could just change that right here right now, because we know minus minus is plus, we can just write 8 quantity squared right there, and of course this is going to be negative 6 quantity squared. So that means we've got 64 plus 36 under the radical, under the square root that is, and we get the square root of 100, so we get a length of 10. For the height, since I use this as my base length, the height can be represented as this length right here, which is Q'd R. So for QR, again, something like that you can certainly do as what I did. I treated this as, x1, y1, and I treated this as x2, y2. And I will also go ahead and treat this as x1, y1, and x2, y2 as well. So that being the case, or that being said, we want to go ahead and find QR now. So using x2 as 0, I have 0, and then I'm going to go ahead and do minus negative 3 quantity squared plus 4 minus 0 for y2 minus y1 quantity squared. So that gets me 0 minus negative 3 is 0 plus 3. So I have the square root of 3 squared plus 4 squared. So here I've got 9 plus 16. Square root of that is going to be the square root of 25, which is just equal to 5. So I have, in this case, everything I need to figure out what the perimeter is. Recall that to calculate the perimeter, all you need to do is take 2 times your base length. So for us, the base length was 10, plus 2 times your height. Why is it 2 times both? Because there's a pair of them in the figure. And when we do that, we end up with 30 units for our perimeter. So that's just kind of talking about how did we find the perimeter of a rectangle in the coordinate plane. This is a great example of that. Recall we also have this example here where we're going, in this case, in the following, Ryan here leaves home, goes to soccer, and then goes to the library afterwards, and we want the total distance. So the strategy here was that we needed to determine the distance from home to soccer. So the home from soccer is this length right here. So we can go ahead and treat this right here as x1, y1, and this is x2, y2. And we want to calculate that length right there. We can call that length hs because it's from home to soccer. And I'm going to use the distance formula to do that. So here I've got -4 minus 0 quantity squared plus 3 minus 0 quantity squared. And so that gets me -4 squared plus a 3 squared. So here I get 16 plus the 9. Square root of that is going to be square root of 25, and so that means the distance was 5 miles. I'm actually going to write down miles just to remind myself that it is in fact mileage that we're looking at here based off of what they just said. So after that, we can go ahead and figure out the distance now from soccer to the library. And I pointed out in a previous video that when you're finding this particular length, you actually don't need to use the distance formula itself. In this case, because you have a linear measurement that is horizontal, which means that you're able to essentially count either visually 1, 2, 3, 4, 5, 6, 7, 8, or if you recall, when we have one-dimensional measurements that we have to find the distance of, really the distance or difference between numbers on a number line, what we can do is we can find that distance d, or if you want to call it SL, that's okay, by taking the absolute value of the difference of the x values. In this case, the x values are -4 and +4. So if you take the difference of a -4 and a +4, what you're really doing is you're determining the overall difference between the two numbers and how far away they are from each other. And so that means we have 8 actually. Now that's actually miles, and it's actually simpler to calculate the length that way, right? Now the reason why we're able to do that again is because we have a horizontal line, right? So whenever you have a horizontal line or even a vertical line, this allows you to think about finding the length one-dimensionally as opposed to two-dimensionally, because you don't have length and width per se. It doesn't have any vertical height to it at all, so there's no incline. So therefore counting the distance is as simple as just looking at how far away -4 is from +4. Okay, so that being said, we have everything we need now to find the total distance that we want. So for the total distance, I'll just call it total. We have our from home to soccer, from soccer to the library. We had 5 miles plus 8 miles, so we get 13 miles. So 13 miles is the total distance that they had to travel. Now for area, we have a rectangle here with given lengths for base and height, and we have to find the product of the base and the height. So our strategy then will be, let's go ahead and figure out what one of the lengths of the base is going to end up being. Okay, so in our case, I'm going to go ahead in red and treat this one as x1, y1, and I'll treat this one as x2, y2. So I'm going to find DC and treat that as my base. So I'll make a note of that. So DC is going to equal the square root, and here we have x2 is 4, and x1 is -2, so 4 minus -2 quantity squared plus -1 minus -3 quantity squared. And remember that we can do negative is positive, negative is positive, so I can fix that up right away. So here now what I get is I have 6 quantity squared plus a +2 quantity squared. So that gets me 36 plus 4 under the square root. so the distance is going to be the square root of 40. And remember, the important point here, the important distinction is that we want to go ahead and leave as a root until the end. We want to leave it as a root until the end, and it's just because we want to make sure that we don't make any approximation errors or mistakes. We want it as accurate as possible. The other length in question that we can go ahead and look at, because we use this as our base length right away, I can call that B. The length over here for our height is going to be AD. I'm going to use that as the height, and I'll call that H. And I guess I'll go ahead and call this, I'll leave this as, well, we'll make this x2, y2, and I'll make this x1, y1. Okay, so that'll be my lengths there. So we have AD, or DA. If you want to use DA, that's fine. I'll just use AD. Square root of, we have our x2, -2, minus -3 quantity squared, plus -3 minus 0 quantity squared. And again, negative is positive. So I got the square root of, we have positive 1 squared there, and then we have -3 squared there. So that gets us 1 plus the 9, so that's the square root of 10. There we go. So to calculate the area of the figure now that we can do that, for the area, the base was the square root of 40, and we're multiplying that by the height, which is the square root of 10. So that's the same thing as the square root of 400. You can multiply the numbers underneath the square root, and the square root of 400 is just 20. So since this is an area, we want to go ahead and make sure to mention that this is square units. I'm going to write my answer up here just because the screen's kind of cutting off there, so it won't let me write. So we've got 20 square units. We're now working with 2 dimensions, and that's why we square our units. For the area of a triangle, we're looking at the figure here, and what we want to do is we want to figure out a plan, and that idea is to first focus on where the right angle would be. So what you want to do is you want to first identify the slopes, right? We can likely see that the right angle in question would almost certainly be right here. So let's take a look at the slopes of the 2 lines first to see which are actually perpendicular. If you count this one right here, it actually goes up a grand total of, in this case it goes from a 1 to a 4, right? So if it goes up from the 1 to the 4, we can count it up. That's a difference of 3, and then it goes over from 3 to 5, which is 2. So if you're looking at the y value, you're counting it up and you're going over to 4. Counting up from 1 to 4, that's plus 3, and then over 2 is plus 2. So the slope of that line is 3 over 2. Then the other one, I guess I'll use red, it goes from 1 to -1, so when it goes down like this, it's only traveling from 1 to -1. Well, that's actually just a distance of -2, or I shouldn't say distance, but rather the rise is -2. And then it goes from 3 to 6. So from 3 to 6, that just indicates that it went over plus 3. So the slope of that line is -2/3. So the point that we're trying to get at is 3/2 and -2/3 are opposite reciprocals. So because they're opposite reciprocals of each other, right, we know that the sides are perpendicular, right? And so the right angle has to be located at 3:1. So there is a right angle at 3:1. Now, why is that important? Well, the reason why it's important is what we're about to look at now, okay? The reason why it's ultimately important is because we need to know what the base and the height is for the triangle so that we can calculate the area, right? Well, in this case, we want the legs of the triangle, the right triangle, to be the base and the height. And so now that we know that that's where the right angle is, those lengths have to be the base and height. For example, I could go ahead and treat this as my height, and then this right here can be my base. So I'm going to allow this to be x1, y1, and this is x2, y2. And then I'm also going to treat this as x2, y2, and this is x1, y1 when I calculate that measurement. So for the base here, we're going to go ahead and find that base. I guess I'll just call it b. That's going to be the square root, using the distance formula, of 6 minus 3 quantity squared plus -1 minus 1 quantity squared. And so from there we can go ahead and we can simplify that as 3 quantity squared, and then -1 minus 1 is -2 quantity squared. So that means I get 9 plus the 4 square root of that, and that's the square root of 13. And remember, we want to leave this. We want to leave it right now. Leave as a root. Don't actually approximate. We want an exact answer. Finding the height now, finding h, take the square root. There we go. So here we have x2 is 3, x1 is 5, so 3 minus 5 quantity squared, plus 1 minus 4 quantity squared. So that means I'm going to get a -2 quantity squared plus a -3 quantity squared, and then I get 4 plus the 9 square root of that, and I just so happen to get the square root of 13. So it actually happens to be an isosceles right triangle, because both lengths are the same, and when you have two lengths in a triangle that are the same, it's an isosceles triangle. So now I can calculate the area of the figure. The area is going to be the base length, square root of 13, times the height, square root of 13, all divided by 2. So it's the average, really, in a sense, not actually the average, because that's a little bit different. We're multiplying here. But we are taking the square root of 169 divided by 2. So in other words, we get 13 divided by 2, which is going to be 6.5 square units. So there it is. There's the area of our triangle. And so now we have used the coordinate plane to find an area of a triangle, find the area of a rectangle, and even look at an application problem as well. So now we're looking at your exit ticket, right? For the triangle application with Ryan, I would recommend that you kind of review that. It's the best, probably I would say most like question to the one we have here per se. Can help you refer to that slide. Having said that though, I also would remind you of the Desmos graphing calculator as well. That can certainly be helpful. Maybe watch out, you've got this, 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 and this. Just think about that and what that can do to help you on that question. What's the perimeter of the triangle ABC? Again, it's not the same thing as area, right? You're finding the perimeter, so remember, worry about what perimeter means. But you might want to think about finding the length of all three sides, right? And then there, of course, is the area of a rectangle problem there. And, of course, there is problems that we've done that are very, very similar to that, such as this example right here, as a little tip for you. Okay? All right, that's going to be lesson 4.09 for area and perimeter with coordinates.